Okay. The second part of the electrostatic thing is the divergence E and curl E. So, and the beginning we're starting to introduce some field line concept and what is flux. And one of the most important things is Gauss law. And then divergence E and application of this Gauss law. And the final part will be the curl of electric field. Let's get started. Okay. Okay, now uh, saying that the field line is actually a idea, just an idea. It's not the real existence of this thing called field lines. But for the historic reason and for simplicity, we'll still consider this concept. So here is the Coulomb's law that we talk about the Coulomb's law telling us that the electric field at a particular observation point and at point R, which is the integration or the sum of the charge distribution, or in this case, the volume density of the charge density distributed in space. And we take the integration through this source distributed in this volume. So we use V plot as the source distributed at this particular point. And then because the Coulomb's law required that funny R, which pointing from the source to the observation point, and the electric field is inverse proportional to the distance squared. Okay, that's it. And here, the prime indicate the source. So when we do the integration, we integrate all the source part. So the prime will be disappeared. So eventually, you will only show the R without a plot or the observation point electric field. That's it. So now consider a single charge Q at origin. So everything is simple. So we just place the charge at the origin. So the electric field will be just very symmetry to the center point or the origin point. So it really depends on where we want to observe that any particular point in space has a distance r from that particular observation point to the origin. So the electric field will be something like this one. And always the electric field is pointing out since the vector is pointing from the source point to the observation point. So it's pointing out. That is the field direction. And the field strength or the magnitude will be something like this one if the charge is Q. So that's trivial. And interestingly, so the field is a vector, is the basic representation because each point using the electric field to represent the electric field. So the electric field has a direction and also the magnitude. So we use that arrow to represent it. But uh, so the vector length represent the magnitude of the field. Of course, you know it. And of course, we can plot 1 over r squared, which is just something like this. And it is diverged at the original point, origin point. So, okay. And it will become weaker and weaker when we move away from the origin. And the field line is actually a concept. It just links the vectors of each point. That is field line. That's another representation. It's more historically. We like to use this concept to help us to understand the electric field and how is the electric field look like or which direction it could go through. The field line density represents the magnitude of the field, not the magnitude or the length of the vector. So this is slightly different, but essentially it's just link the vector. So if you pointing to this direction and then we reach some point and pointing another direction, so just link everything together, you become a field line, what we are talking about. Also, the field line also give the direction of the electric field direction. So that's easy enough. Okay, so field line does not really exist, just a convenient way to represent field. Okay, And also historically, it's easier to visualize it, but it's not a good physical idea to do it. And much later, we'll throw away this concept when we talk about magnetic field stuff, but that'll be later. Dense field line represent higher field magnitude. Like this one, here is more dense, here is more loose. So we'll consider at this part you got stronger electric field, qualitatively, not quantitatively. Okay. So field line is commonly used to represent complicated field distribution. That's why field lines start at a positive charge and at negative charge. So that's the idea. Or from to infinite far. So if you have a positive charge, so you'll go to the infinite, not necessarily go to the negative charge. Something like this. So same thing for the negative charge, probably from infinite to here. Apparently, this line is definitely go to infinite, right? So that's the idea. Field line should be drawn symmetrically in the vicinity of a charge. Okay, so at the very nearby region of a charge, the field line should have the equal spacing, so there be uniform or symmetry around the vicinity. Vicinity is the nearby part of a charge. Okay, field line don't cross. There's no cross field line things. Okay, two field line will not cross together. That's it. Field line numbers should be infinite, but we draw only a few. So that's the more uh, uh, reasonable thing, because there's any particular point, you always can find the electric field. So you always can link the line and got the new field line. So it's infinite in general, but we don't have time to draw everything. With finite numbers of field lines from a charge, draw double the field line if a charge is doubled in the same plot. So that's it. If you have double the charge, so your field line will be double. That's it. That's the way you represent the strength of the field line or the electric field. So here are just opposite charge. So charge field line from positive to negative, positive to negative. That's it. And both are positive, and they will just go to infinite. And there's no crossing of the field lines. Okay. Flux. Flux is somehow coming several places in physics. Flux describe any effect that appear to pass or travel through a surface of substance. So whether it actually moves or not, it just goes through. That's it. So the effect here is describing a physical quantity. Even a light coming through certain surface is okay. The surface, a sound or even particles goes through a surface. And you can consider a door is a surface. So you go through a door. It can be also considered a flux. Or you always say that water flows through a pipe, and a certain part of the pipe is a area. So you can consider how much water goes through. That's a flux. It doesn't matter. So example, water flows through a pipe. That's the idea. In electromagnetism, flux usually using a symbol this capital phi. Okay? And since we flow through an area or surface, so we flux electric field through a surface S. This is funny S. Okay, now, so we write down the flux of electric field as the electric field flows through an area S. So we only consider the normal direction, since we just consider we go through it. But if we go through an angle, we just don't consider it. So the surface normal vector direction and the physical quantity here is the electric field. They are both vectors. So we just consider the projection along the surface normal direction. So note, dot product, only the electric field component along the surface normal A cap direction is integrated. That's it. So here is the definition. So that's it. Somehow this electric flux counts how many field lines passing through this area. If the surface is a closed surface, the flux measures the total charge through the closed surface. Within the closed surface. This is actually the fundamental statement of Gauss law or the Gauss idea, how the flux is imagined in this kind of electric field of a certain volume. So, in other words, counting total number of field lines from the charge is actually counting how many field lines coming through the surface will give us the idea how much charge is within this volume. Okay, what does it even mean? Okay, so if a charge is in a closed surface, if your charge is in a closed surface, okay, the field line must pass through the surface somewhere to reach the infinite far. So this surface is just, you can imagine a surface. It's not necessary to exist a surface. But Gauss is just considered as a surface in space, which is not something really exist. We just consider a certain surface. That's it. And it doesn't necessary to be something there. Okay, so in other words, it is not a plastic shell or metal shell. No, there's nothing there. It is just mathematically, I want to define a surface somewhere in space. I can define a sphere somewhere here. I can define an ellipsoid somewhere here. It doesn't matter which direction. It doesn't matter. There's nothing here in the space. It's fine. I just define a closed surface. And then if we can imagine the field line going through, and we will count it, okay, one field line. All right, that's the idea. So if a charge is outside the closed surface, a field line may pass through the surface somewhere. Okay, so if there is surface here, for example, like this can, okay, this is the can has a surface, but not necessary to be a physical existence, but we have a surface, for example, just like the soda can. So if you have a charge here, so it generates a field line going everywhere. So one might be penetrating it, but since it is just an imaginary surface, it will go through it, enter the can, and you'll go out somewhere. That's the idea. But if a charge is placing inside the uh, the the can, so the field line will go out to infinite. So it just generate several field line goes through this surface. But now here a field line going in and coming out, we'll consider this zero because it go one in and one out. There's no uh, total sum. So go in plus one, going out minus one, so it will be zero. But if you have a charge inside this surface, everything go out. So you just count 1, 2, 3, 4, 5. So you count so many. That's the idea. So we are counting how many field line going through, flow through this chart, this imaginary surface. Okay, so counting the number of outgoing incoming field line corresponding to the total positive negative charge within the surface. This is the basic concept of Gauss law. So here, let's see it. Okay, here, if you have a charge, if you got the imaginary surface, so the flux is actually the field line and in a product with this tiny area, which is the flux. So if you have a closed surface, which means there's no opening, so the field line goes through it and it must go out somewhere. So go in must go out. Whatever go in must go out. But if you have a arbitrary shape. So you have a total charge here. It just simply go out to infinite. So you just count it 1, 2, 3, 4, 5, 6. So there are totally 6. And regardless what kind of funny shape you have, you just coming totally 6 anyway. So you consider the regardless what kind of shape you have, you always have the same number that of field line going out this service. And also, if this service contain positive and negative charge, your charge field line from positive negative, positive negative, and also it go out. So here are 3 goes out and 3 come in. So there'll be totally 0. So here, just considering there'll be no total charge inside, even though you have positive and negative. So totally, the total charge will be 0 within this volume. So that's the whole idea. Okay, so counting the number of outgoing and incoming field line corresponding to the total positive negative charge within the surface. That's the idea, the basic concept of Gauss' law. So consider a charge at the center of spherical surface. So here, this spherical surface is just what we call the Gauss surface. We try to imagine one surface, which is spherical surface. So we just consider we have a surface that would take the integral of the flux. Okay, so that is the idea. So we take the closed loop integration of the electric field as a flux flow out the surface. Okay, that's the idea. So that we're using the Coulomb's law to write things down like this one. So since we just simply placing the charge, at the center, so we just replacing use the we just write down our surface element r squared sine theta d phi with the direction along the r direction. So we got r cap. So r cap, there will be no more vector here. So doing the same thing, we just remove, and doing the integration, and from phi will be from 0 to 2 pi, and theta from 0 to pi, that kind of thing. And eventually we figure out this entire thing equal to the charge divided by the electric permittivity, what we mentioned earlier. So this is the enclosed charge. So this is just a simple conceptually proof that it works for a point charge at the origin. Of course, it could be proven that regardless your shape will be spherical or not, regardless the charge is located in everywhere, this will be proved. That will be the Gauss law, which the integration of the flux through the enclosed surface will be the total charge divided by epsilon now. That's the idea. So the Gauss law is if multiple charge is within the closed surface, so the electric field will be the sum of each charge contributed electric field. So based on what we said, the principle of superposition, so because the electric field can be summed one by one, that's it. So our electric field just writes things down by summation of each charge contribution. So there'll be something like this. So in other words, this is the sum of the total charge. So we use a subscript ENC called enclosed. So in other words, the surface integral of the flux through this surface is the enclosed charge divided by epsilon now. This is Gauss law, or this is an integration of Gauss law. And with that, this is some important result, and we pretty much use it quite often. And later on, we'll see how often it is. Okay, now, but also we know the divergence theorem, because divergence theorem has something take the divergence and do the volume integral equal to the closed surface integral of the surface integral. So you can see this side is equal to this side. All right. So on the left-hand side, we will do something interesting. Okay, so we just replace V by the electric field because V here in the divergence theorem is just any kind of vector will satisfy this relation. So now we just write things down. Like here we have the uh, electric field. We just write electric field equal the total charge and the electric field. Okay, so the total charge is actually the volume integral of volume charge density integrates through the volume that containing the charge. So that will be the enclosed. So this volume, how much charge enclosed in this closed surface. So in other words, these three things sum together will be something like this. So both volume integral will be something like this. So the only possible thing is these are the same. So divergence electric field equal to the charge density divided by epsilon naught. So this is Gauss law in a differential form. That's the idea. Here, these two are both Gauss theorem. One is integration form, one is differential form. This one is harder to understand, but this one is very visualized. You got the electric field penetrating through the surface, enclosed the surface. So the electric field flux by counting or doing the integration will tell us the total charge enclosed in this surface. That's the idea of Gauss law. All right. So now, since we have the divergence E, we can put our Coulomb's law into the exam. So from the more general form is the Coulomb's law. The Coulomb's law, just like earlier we have, is just uh, simply the I, I cannot do it. Okay, so simply what we have earlier, the Coulomb's law is the integration of the charge density through in the space. Okay, sorry, this should be V prime, so I fix it later. So the V prime, so this is the charge density of what we are worried about. So the electric field at the observation point is something like this. So we take the divergence of this electric field. So we just take the divergence since the divergence only work uh, on the observation point. So you're moving, so we will figure it out. That's whatever consists of R will take the divergence. So we we will do this. And earlier we talked about this divergence actually give us 4 pi delta function cube with this funny R vector. It's a three-dimensional delta function. In other words, here we just rewrite our funny R vector into this R minus R plus. So here is telling us this is this is exactly telling me the charge distribution. So this integration of three-dimensional delta function of this thing is just moving the entire thing, though replaced by this R without prime and into something like this. And this proves the Gauss law is in differential form. Again, that's it. That's the official proof of Gauss law. Okay. So here is some additional remark. Even though this is not in the textbook, and I would like to remind you something, but maybe you are not going to use it later, but maybe you will. Anyhow, so here we just talk about taking the divergence of this thing equal to the delta function whatsoever. And take a look at this thing. This divergence is a linear operator, and here is a function. and this is delta function. And the structure of this thing is extremely important for mathematically solving some differential equation, especially physics related. So here we can take a look at it. The thing. Whatever calculation that make a delta function is important. This is the idea. You need to be very careful. Delta function is something extremely important for solving a differential equation because this function is the key to solve the inhomogeneous equation. This function is called Green's function. This function is called the Green's function. General form of a linear inhomogeneous equation look like this. So you have linear differential operator and you have a field n equal to the source. In other words, the source will generate what kind of field. Okay, so if I have a field, I simply take the linear differential operator, I will get the source. Okay, but typically, the difficult part is we know the source, but we need to know the field. That's the difficult part. That is the very difficult problem we usually encounter, especially the source is funny looking shape. Okay, so typically the difficult problem is we know the source, but we don't know the field. Okay, so U is to be solved. This is the difficult problem to solve. So if we give a source function, source distribution, we want to know the field. Delta functions serve an important role. So given the source information, obtain the field is very difficult to solve in general. So if there's a G function that make the linear operator operate on G function equal delta function, then the field that something we want to solve is just simply our source, funny distribution or not, taking a convolution of this particular function or so-called Green's function. So I solve the difficult thing, the field distribution, in this way. This is called the Green's function method to solve an inhomogeneous differential equation. So the inhomogeneous means this source is not zero or there's some source. Then it is difficult to solve the field. That's the thing. So this is a very important method for solving inhomogeneous differential equation. We will come back later or not. We don't know, right? So because later on you are going to encounter several differential equation, and this is a method that will give you go far. That's it. All right. So let's continue. So the application of Gauss' law is indeed okay. Gauss' law is powerful, even though it is a very general form that, well, regardless what kind of shape you have, as long as you count the field line, you know everything. You know whatever the charge in it. But it is not necessarily particularly useful. Usually, a symmetry source and a symmetry Gauss surface can lead to easy to reasonable calculation. So symmetry geometry is important. Symmetry source, symmetry Gauss surface choosing. The Gauss surface is what we choose because Gauss doesn't limit it our choice. We can choose spherical, cylindrical, and even box to solve the problem. But there's always some better geometry for us to solve the problem. So based on the geometrical symmetry, we should choose properly to make the calculation easier. So typically, spherical symmetry, we use spherical Gauss surface. Axial symmetry, we choose cylindrical Gauss surface. Planar symmetry, we choose pillbox. Okay, pillbox is something like this. Cylindrical is something like this. And spherical is spherical. That's it. Otherwise, numerical method is required. We need to use a very different numerical method to solve complicated things. So we when the electric field is not perpendicular to the Gauss surface, a lot need to be done. You need to do the projection, you need to do crazy things, and the calculation will be very, very troublesome. Anyway, so that's it. So here is an example uniform charge solid sphere. So if you have a total charge Q and uniformly distributed inside the sphere, and the sphere radius is capital R, and we can choose the Gauss surface. Again, Gauss surface is something you choose. It is not necessary to be some physical existence. You just choose the surface. Choose Gauss surface with radius R. Enclose this charge distributed sphere. Okay? So the charge is inside. We just choose the surface, cover it, and also center at the same point. Okay, so this Gauss surface has radius of r, small r. Due to the symmetry, the electric field is outward, is pointing out, normal to the Gaussian surface, and the value are the same along any direction. So the electric field pointing out, pointing out, pointing out, pointing out, all perpendicular to the Gauss surface. So the calculation will be easier. So now that's it. That's the idea. That's the integration form of Gauss law. Is the electric field flux through this enclosed surface is the enclosed the total charge divided by epsilon naught. That's the idea. So now we just put it in. So we choose this Gauss surface enclose the total charge. So that's it. So in this case, we just since it's normal, so the inner product can be removed, and the A will be 2 pi r squared. That's it. So that's the surface area of a sphere. And here the Q is the total charge. We just write things down here. So now we know the electric field, the magnitude is this much. And we know this electric field pointing out. So we just put back the radial unit vector. That's it. And interestingly, this is exactly like a point charge Q at the center. So if you have a uniform charge distribution in a sphere, you can consider just a total charge at that original point. So that's it. That's perfectly fine. And Gauss law allow us to consider a spherical uniformly distributed charge can be equivalent to just a point charge at the center. That's perfectly fine. So that's the important result here. And similarly, a non-uniform charge cylinder. So this volume charge density is proportional to the radius. So you have charge, well, more on the outside and zero at the center. So this is the uh, this thing is the charge distributed here. So we can try to figure it out. What is the electric field anywhere inside this cylinder? So now, this Gauss surface we choose just inside this charge distribution. Well, Gauss law didn't say we only can choose a vacuum somewhere no material. Gauss surface can be anywhere as long as we like. So here we have the charge density, volume density. We write it down. And we find the electric field as a function of S in the cylindrical coordinate. What is the charge along this radial direction? So still, using the symmetry, we choose a cylindrical Gauss surface like this one, and we take a particular length here, doesn't matter. I assume this is infinitely large, and we probably have a good idea the electric field just pointing out. So again, electric field pointing outward, normal to the Gauss surface. So that's fine. And we just write things down, the electric field, since we choose wisely, very smartly, we choose the Gauss surface normal to the electric field. And no electric field along these two circular area. We just need to consider a cylinder part. So the surface area is 2 pi s times L is the total area. Okay, so that will be the enclosed charge inside this Gauss surface. So we just write things down. So this encloses the charge. Here is the volume integral of your charge density. There'll be something like this. You just can go through it. And integration from 0, s equals 0 to s, any particular s. So s part, we always indicate it is the source part. So the s part is something like this. So we just do it and got this result. And to handling the equation, so we know the electric field, the magnitude will be this much. And also we know it pointing out. So we put back the unit vector here. So that's the idea. All right. So same thing for uniform surface charge on a plane. So a plane, we will choose pillbox. So that's the idea. The pillbox, yeah, will cover both sides of this surface. So we have a uniform surface charge density, sigma, is coulomb per meter square. Choose Gauss surface as a pillbox, so it will be still the same thing. Okay, within the pillbox, so the total charge is surface charge density times the area. So this is the area we choose. The electric field is perpendicular to charge surface. So because symmetry, so always the electric field point out from the surface. So it will be along the surface normal direction. Okay, so on the pillbox surface, there's top one and the bottom one. You cannot see it. Yeah, you probably see the very light gray part of this box. So on the top, you'll go up. On the bottom, the field go down. That's it. So the electric field times the area. So just write things down. On the side of the pillbox, electric field parallel to the Gauss surface. So there's no sideway. There's no electric field along this four surfaces. So don't worry about that. Therefore, taking the surface integration of your electric field, there'll be the total charge divided by epsilon naught. That's it. So here will give us the electric field is proportional to the surface charge density divided by 2 with epsilon naught. And of course, the electric field has to have a direction normal to the surface. So interestingly, it is independent to the distance. So yeah, that's the idea. So wow, this is an important example. Is if you have two parallel plane, each has a charge density. One is positive, one is negative. So earlier, when we have the result here, just like the electric field on both sides is this much, and positive and negative. So each one, like this is positively contribute to the electric field. This the positive contribute to the electric field. We just look at this one. Okay, so it's go this way, and since superposition, we don't care about this at this point. So even though beyond the location of the second plane, the electric field still remain the same magnitude and along the same direction. However, on the other side, the negative surface charge plane will have electric field pointing in and also pointing in. And the superposition tells us we can sum things together. And take a look at it. In this region, the sum, since the charge density is the same, so the electric field is the same. This going out, this coming in. So the sum will be 0. On this side is also the same. But here, within this two plate, this is the total electric field. So the electric field only exists in between the plate. That's the idea. Or twice one plate contributed. So it'll be twice. And this is some important thing. This structure will be known as a capacitor later. So we'll visit it later in, yeah, much later. Anyway, so the capacitor is actually, you use it in the circuitry, electronics, that kind of thing quite frequently. It's one of the most important basic component of circuitry. So we'll come back later when we talk about material fitting inside that kind of things. Anyway, so the second part, the curl E. Curl E is actually slightly more difficult to deal with it. Placing the charge at the origin, again, we write things down. The curl E will be 0. That's trivial. So because take a look at it, and basically you can easily prove it, curl E equals 0. And try to do the integration form of Gauss law by replacing the L into something like this. You can try to do it. And the electric field is symmetry and pointing out, and no component along theta direction or phi direction because it plays in the center. So there's nothing you can do along these two part. So it'll be easy. So with that, okay. So we take the line integration from A to point B. We do the integration from point A to point B. So it'll be something like this. So there'll be something like that. So this electric field along certain paths to do the path integral. It is only in the initial point and final point is important. So it's path independent or independent to the path of your line integral. So this is a conservative field. So earlier we talked about it. So it doesn't care about which path you follow. You always have the same result. This is a conservative force field. And with that, okay, if the path is a closed loop, earlier we also talked about it, the initial point coincides with the end point. So closed loop means there's no beginning, no end. Okay, so closed loop. So this integration must be 0, or we write things down. It's a closed loop path integral. It'll be 0. Okay, then we recall the Stokes theorem. Okay, so this entire thing can be replaced by the surface taking the curl of this field. Since this is 0, this is 0. So whenever it holds, the curl E must be 0. So, well, that's the idea. So point charge at original case is something like this. Still hold for the charge at different location. So the principal superposition make the conclusion still hold for the multiple point charge. So you have total charge contributed by each charge. So taking it, and each has a curve